And so I was not really well prepared today, and uh, of course, we are going to a little bit slower than I expected, so we have to rush today. We have to go faster, a little bit faster, maybe not too much. But I shall give you something that I missed last time. We spoke about the greatest common divisor and Euclid's lemma, and we discussed some exercise, but actually I didn't give you any way, any method, any procedure to find the greatest common divisor of two numbers. Now, I recall very briefly what is the greatest common divisor of two numbers, integer numbers, whole numbers, A, B. We can assume even that they are positive. This greater divisor is just a divisor which divides both, of course. So D divides A. Oh, sorry. Uh, sorry. Here it is. So D is the greatest common divisor of A and B when B divides both A and B. No, this is another, this is the proof. The definition is elsewhere, but so D divides both A and B, and it is the greatest. That means that if the prime has the same property, that is, divides both A and B, the prime also divides D. So D is the largest one, in a sense, with respect to divisibility, and also because it's largest, of course. So, how to find the greatest common divisor of A and B? The key observation is the following. Is the following claim, following back this one, and it is really powerful. This statement, you will see, maybe probably with Paolo Franciosa, I think so, that what I'm going to explain can be solved with one line of recursion from a computer scientist point of view. So, but the recursion implements exactly what I'm saying now. So, which is the key property is that if D is a common divisor of A and B, then D is also a common divisor of B and a smaller number than B, R, where R is the remainder of the division of A by B. So, the greatest common divisor of A and B is the same as the greatest common divisor of B and R, where R is the remainder of the division of A by B. Just a few words about this property, which is, before proving the property, let us discuss the algorithmic consequences of this fact. So if you are looking for the greatest common divisor of A and B, just look for the greatest common divisor of B and R. But now you are in the same situation as above, as the original question. So you can again divide B by R to get another remainder, which is smaller, because you should remember that if you divide B by R, you have a quotient and a remainder R1, where R1 is non-negative and is strictly smaller than R. So we are not we have not already proved this the highlighted the highlighted equation identity. Sorry, but assuming that this is true, I'm going to give you an algorithm to find a procedure, a constructive way to produce, to yield the greatest common divisor. So you start with A and B, then you look for the greatest common divisor of B and R, and then the greatest common divisor of R and R1, and so on and so forth. So what is nice is that since this property holds, the sequence of successive reminders you find during the execution, let's say, of the algorithm is strictly decreasing, and they are non-negative. So you have a sequence of integer numbers which are non-negative and strictly decreasing. So if I say R, you must say a smaller number than R. There is another one among you that should say another smaller number. So there is one among you that must say 0. So the sequence must terminate in a finite number of steps. And it terminates, of course, with 0. The the last but one element in the sequence is the greatest common divisor, and this is written here. Now we do an example from scratch, but to clarify, but I want to show you why this identity is true. And it's very easy, and it depends on Bezout identity, on the definition. We worked it out. We try to work it out with the help of the exercise from 1 up to 4 Bs. The claim is that the greatest common divisor of A and B is the same as that of B and R. Why this is true? Because if D divides, so I am assuming now that D is the greatest common divisor of A and B. And I'm going to show that D is a divisor, not necessarily the greatest, the greatest one, but it is a divisor of B and R. And then I will show that if D prime is the greatest common divisor on B and R, then it divides also the greatest common. It divides also D. So we have D divides D prime divides D, and we must conclude that D is equal to D prime. So let us start with the greatest common divisor of A and B. So D divides both A and B. So D, if D divides A and B, D divides any linear. We saw we saw this fact. If D divides A and B, divides any linear integer linear combination of A and B. So in particular, it divides A minus BQ. So this is a linear integer combination of A and B, where it is written in this way. S is equal to 1. Sorry. This is B. is not Q, sorry. And T is equal to minus Q. So this is a linear integer combination of A and B. But what is A minus BQ is exactly the remainder of the division of A by Q. So D divides both R and B. So D divides D prime, which is the greatest common divisor of B and R. Conversely, let D prime the greatest common divisor on B and R. By the same reason, it divides both, so it divides any of the linear combination. In particular, it divides this linear combination. But what is this linear combination? Is A here S is 1 and T is Q. And so D prime divides D. And we have both the relation as required, and we conclude that D is equal to D prime. So this is, I should have upload these notes. I swear I will do. I let you check this exercise. We let us do an example together with easier numbers, but maybe it's more instructive. So take A 20 and B is say 9. We want to find the greatest common divisor of 20 and 9. Everybody of you knows that this is 1, of course. Let us check that the algorithm works. And so which are the steps of the algorithm? Start with 20. Put an underline under the quotient, sorry, the dividend and divisor and the remainder to keep it highlighted during the course of the algorithm. So 20 is 2 times 5 is 9 plus 2. And this is the first pair. So what the algorithm says now is to divide 9 by 2. So it is 4 times 2 plus 1. And we are done essentially. Because now what the algorithm says to divide 2 by 1. So and this is the last but one is the greatest common divisor. So it is a very, very nice algorithm, and especially because it can recursively implemented, so it's also very efficient. But what is most important for us is the reverse procedure. Here is the common divisor. Now we know that the greatest common divisor of any two numbers A and B is always, by Bezout identity, a linear combination of the two numbers. So 1 must be a linear combination of 20 and 9, of course. How to find the coefficient S and T of a Bezout identity, and why? And why should we find this coefficient? How? We will see in a moment. Why? It's because this is the way we compute inverse, arithmetic inverse in in the residual class ring. We will see. We will see in a while. So this is a very, very important procedure. This is a very, very important property. If you want to invert class of 3 in Z5, you must apply this. You must apply this construction. So here we see how to find the integer linear combination, the integer coefficient defining the linear combination, defining a Bezout identity. You start with the last but one row. Here you see this is the row. You are looking for an expression which has the greatest common divisor on the left-hand side, and on the right-hand side, you must find a linear combination of the given numbers. So from this row, just just in a very simple way, you get the following identity. So 1 is 9 minus 4 times 2. Now, 2 is the remainder of obtained in the step of the algorithm at the previous step. So you can apply the same. You can apply the same strategy, and therefore you can express this 2, just by looking at the row in which it occurs for the first time, which is the row immediately preceding. And you can express 2 in terms of the other numbers. So you get 9 minus 4 times. You put you transport 2 times 9 on the other side. So 20 minus twice 9. I forgot the underline here. Let us do this simple calculation. 9 minus 4 times 20 plus 8 times 9. Let us group. Minus 4 times 20 plus 9 times 9. Here we found the coefficient. Oh, sorry, I forgot again the underline. Here we found the coefficient S and T of the linear of the Bezout identity. So eventually we get as a byproduct an even more interesting result, that the same algorithm that finds the greatest common divisor of two numbers also finds the linear integer coefficient defining a Bezout identity. And this will enable us to invert, to produce arithmetic inverse of residual classes in the theory of modular arithmetic. So this is what was left last time. Now start with the this new subject, and these are prime numbers. So I don't want to insist to prime number because in this place I'm not a number theorist, and in the second place we don't need much more than the definition. However, this is a good occasion to get familiar with primes, at least to start the knowledge, the basic knowledge about primes. And so we give the definition, and then what I'm just a proposal. I give you a number of exercises with hints. You can try to solve some of these exercises. Some can be challenging, but you can you can ask to your tutors help anyway. Of course, they are not mandatory and there is no obligation. So you can do it if you like. If you don't like, just keep it. But it's a good occasion to to learn something that maybe you don't know yet. So let us start with the definition, and let us look to the easiest one, which is also the most assertive one. Is this one. Originally, I thought to give a more abstract one at the beginning, but this is more efficient in this way. So a prime number is, of course, an integer number, a positive integer number, which has the following property. It has just two trivial positive divisors. So a number is prime whenever it is its divisor are exactly 1 and the number itself. But look, we are excluding, this is important, we are excluding 1 with this definition from the set of prime numbers. So 1 is not prime. The number 1 is not prime. I don't want to say more about that, but just me say that this is not, how to say, inherently natural, an intrinsic factor of nature. No, it's not. One could have been prime, could have been not. It has been considered for a long while prime, even by greatest mathematicians like Harvey. Maybe some of you saw the movie. I don't know what was the English original title. Maybe it's something like The Man Who Saw Infinity. It was a movie about Ramanujan, but Hardy, who was his mentor, was his mentor in the movies and also in the reality. He kept thinking that 1 was a prime number. So modern mathematics excludes 1 from the set of primes. But this is just a matter of definition. Has nothing to do with nature, God, or magic, or the constellation. Nothing to do. It's just a choice, which is the most efficient one for the modern mathematics, but it's just an axiomatic choice. So prime, one is not a prime. Yes. There is, so what is the importance of prime? That they are somehow atomic, even if there are subatomic things now, but let's say the smallest brick by means you can construct everything. And they are not, by this definition, they are not further divisible. So in a sense, they are really a whole. But let us look at this fact, which is rather obvious. No. So look at this trivial example. 9 is not prime. 15 is not prime. 9 does not divide 15. However, 9 and 15 are not co-prime. 9 and 15, the greatest common divisor of 9 and 15 is 3. This cannot happen with prime numbers. There are only two possibilities. Either A is a multiple of P. You see, P is a brick in A, or A and P are co-prime. They are not common divisors. This is obvious, but explains why prime are important. What happens to non-prime a number which is not prime is said to be composite because a composite number can be always written as A times B for two integer numbers A and B, with A and B different from one. So a composite number is a number which is not prime, and therefore it has two positive divisor, both different from one. So primes are really different from the other numbers, because this is called composed. A number which is not prime is called composite, just because of the fundamental theorem of arithmetic, because it can be uniquely reconstructed knowing its prime factor in prime factors. So another easy fact is about primes is that maybe you recall, you should, Euclid's lemma. Anyway, what Euclid's lemma says is that if I divide B and B times C, and A and B are coprime, then necessarily A divides C. This is very easy for prime numbers, because in this case we have just so when A and the prime number are coprime provided the A is not a multiple of P. So by applying Euclid's lemma, simplify when you have a prime, and using this observation, you can prove the following fact, which can be assumed as another definition of prime numbers. But look, it is very, very nice, this property. Suppose you have a product A and B, and let P be a prime number. So if you know that P divides A and B, then P cannot divide uh, then P either divides A or B or both. Stated in another way, if you know that P divides A times B, then if you know that P does not divide A, then it must divide B. Um, just think a little bit about this. It are only trivialities, but do some experiments, try to convince yourself inside. So, and this is the most important result about prime numbers, which says that every integer, uh, of course, again, there is a mild request. The request is that the condition is that this work whenever n is positive and different from 1. But for any such number, there are primes p1, pk, such that n can be written uniquely as a product of this prime, of these primes. Of course, these primes can occur more than once in the factorization, so you can raise it to the appropriate power. But when you do that, this expression is unique and depends only on n. Of course, the factorization is unique up to permuting, so the product is commutative, so you get the same expression, just switching P1 and P2 in the respective position, but no more than that. Now, with this, we can content ourselves with this few notions about primes, but let me say something more, which is mostly up to you. I content myself just to read the exercise, to maybe comment some hints, but this is up to you. So the first exercise is about the infinitude of primes. So there are infinitely many primes. Why? There are several, even topological ones. There are several proofs of this fact. I think that what I'm suggesting is used to Kummer, actually. Even it is very similar to Euclid's 1, however, which is a way to an idea to prove the infinitude of primes is by contradiction. Of course, you assume that to get a contradiction, you have to negate the conclusion. The conclusion is that the primes are infinitely many, and the negation is there is a finite number of primes. List all these primes, and when you have listed these primes, you can build another number and capital N, which is the product of all the primes, because they are k plus 1. Now, yeah, but this is a tricky, because I saw that there are places where already at this point a contradiction is got. However, it's not true. This is not the right the right way. You have just a number which is at least 3. So n minus 1 is at least 2. This is what you can conclude from this expression so far. Now, there are two possibilities. Either n is prime and you put, and this is possible because P1, Pk are the only primes, so n cannot be prime. But the fundamental theorem of arithmetic says that there is a prime dividing n. Of course, this prime dividing n can be so that among the first k. Here is the hint. I let you is almost the solution, this hint, is most the proof, this hint, but work out the details to get familiar. There are also famous prime numbers. There are Mersenne, Fermat, there are several others. So, pick I didn't write what the Mersenne number is. Consider numbers of this form when n is prime. Number of this form when n is prime are called Mersenne numbers, not Mersenne prime numbers. Even if n is prime, is not granted that the corresponding Mersenne numbers is prime. So the Mersenne prime numbers are those Mersenne numbers which also are prime. Now, here is what I propose. What I propose to show is that if 2 rises to the power of n minus 1 is prime, then n is prime. This is what you can deduce from Mersenne prime numbers, and also you can use Mersenne prime to define or to advise a primality test. But the exercise is not really difficult, provided that you observe the following identity and proceed by contradiction. So the identity says that if you pick a base number a, integer number a, which is at least 2, and you raise it to the power of p times q, where p and q are integer at least 2, both, minus 1, and you subtract 1, then you have this identity. You can write this expression, a raised to pq minus 1, as the product of two numbers. So what can you deduce by this equality? Immediately, you can deduce that a rises to p times q minus 1 is not prime. Why? Because it is composite. It is the product of two integer numbers, both greater than 1. Strictly greater than 1. So, if you replace 8 by 2, you can conclude that if this number with 2 in place of a is prime, if 2n minus 1 is prime, then necessarily n is prime. Otherwise, if it were composite, you can use this identity to show that the whole number is composite, contradicting that the Mersenne number is prime. So you are assuming that the Mersenne number is prime. This is the nth Mersenne number. So if Mn is prime, n is prime. This is what you have to prove. And we said that the converse is not true. Here is stupid examples. I didn't check, I just quoted from the web. Should be not prime. Check it. So it seems to be the smallest Mersenne number which is not prime. And something more you can prove, maybe you know the story about the suicide of Pythagoras. When he got known about the rationality of the diagonal of the square of side 1, you can prove that the square root of each prime is not a rational number. So why I'm proposing this exercise? Not because you are interested in rational or irrational numbers, but rather because the proof itself is a good exercise. As for the case of the Mersenne number or the infinitude of prime, any of these exercises is not interesting for us, and for you especially, because of the consequences which are important, but rather because the proof itself gives you tools to manage these prime numbers. So look, what I'm really interested in is in this observation. So of course, if P were, the proof is by contradiction. So if you assume that P, no, the square root of P is rational, you can express it at the ratio of two integer numbers, co-prime integer numbers. So, of course, if this is true, it is true that B times P squared is equal to A. No, now let us focus on this identity and think of the fundamental theorem, the unique factorization here. So on the left-hand side, you have the square of A, and the exercise tells you that if P is a factor of a prime factor of A, then P squared is a prime factor of A squared. This is the fundamental theorem. Just think a bit about the fundamental theorem. So, if this equation holds, this equality holds, it's not an equation, sorry, P must occur an even number of times in any factorization or in the unit factorization of A squared. It just apply the fundamental theorem of arithmetic. So from looking at the left-hand side requires P, of course, B squared should must con should con could contain B, but it does not, because A and B are coprime. So if P is a factor of A, it cannot be a factor of, oh sorry, is B squared times P equals A squared, which is this one. Good. However, anyway, they are coprime or not, since P is a prime factor in a square, it must occur an even times, an even number of times. However, it cannot, because every factor of B squared must occur already an even number of times. So the exponent of P in the factorization must be at the same time even and odd, which is impossible. Think about that. Think about that. Now, here it is another exercise, the sieve of Eratosthene. In Italian is Crivello di Eratosthene. I don't know. This is the easiest one method to find the prime numbers which are not greater of a given number n. I let you read the step of the algorithm. So you fix a number n, say 27, and you start writing all the integer numbers between 2 included and 27 included. You just write this number. Pick pick 2 and mark it. Just put the chain, color it, and circle it. Just mark. When you do that, when you have done that, just delete from the list all the multiples, all the even numbers up to 27. Now we have a reduced list, which means all the proper multiple of 2. You can pick the smallest unmarked element in this list and mark it. We know that this smallest element is 3, but in general, we don't know which one is it. So pick the smallest in the smallest unmarked element in the list and mark it, and elect all the proper multiples of this marked element, and repeat until. And this is the tricky speed up of Eratosthenes' sieve. The tricky speed up is that you can confine yourself to those mm, uh, to those currently marked element in the list which are not greater than square root of n. Now, the exercise consists in showing that Eratosthenes seed works. That is, it correctly lists all the prime numbers which are not greater than n27 in our case. Here are a couple of hints. It's not that trivial as it may look at the first glance, but you, you will enjoy, because this is algorithmic, and this is a very tricky speed up. No, this is very tedious. This is the way I think you were taught to the greatest common divisor and least common multiple. I think the standard way is to introduce these numbers through the unique factorization theorem. So you start with we know how to find the greatest common divisor via Euclidean division now. We know that this is efficient because we have you will see, but we already experienced that we have a powerful algorithm, a recursive algorithm to find the greatest common divisor. But I think you were taught greatest common divisor in this way via the factorization theorem. Pick these two integer numbers A and B, write down their unique interfactorization, and then you define the greatest common divisor are the product of the common primes, each one taken with the smallest exponent in the two representation, and the less common multiples are the distinct list of the divisor, each one rises to the largest of the two exponents. So here are the technical details to prove what you know already. I let you think about this. It's quite tedious, but at the end, the gift is this simple formula for the greatest common divisor. But look, this is only seemingly simpler than the algorithm we saw, the repeated Euclidean divisions, because look at the denominator, you have to find the least common multiple. So it is exactly as difficult as finding the greatest common divisor, knowing the unique factorization theorem, which implies that you have to recognize, first of all, you have to recognize whether or not A is prime, which is primality test. And then you have to produce, and you can do that by Eratosthenes seed, but it is very expensive from a computational point of view. So this, just to say that this formula, if we knew only this formula, we were stuck because it's not at all efficient. It by no means efficient. So thanks to Bezout, thanks to Euclid, we have a very, very efficient way to find the greatest common divisor without knowing, without using, without explicit reference to the fundamental theorem of arithmetic, which is very, very hard to realize. Now, my proposal is to stop a little bit. We have a rest, 5 minutes rest, and then we start, which is something which is funnier. And we are talking about congruencies in Z. So, what is? So we stop for a few minutes. See you in 5 minutes. Say, see you. So good. I hope you enjoyed your rest, but yes. Mm, we have to start again. So good. Just me say something that I forgot. Of course, in the representation of using the fundamental theorem of the arithmetic, however, it is really transparent when two numbers are coprime. They are coprime when the set C, which is the set of common factors, prime factors, is empty. And using this fact, you can immediately deduce that when A and B are coprime, their lower common, the lower least, lowest. I say lowest because there is another notion, but in the theory of orders. However, the least common multiple of A and B is their product whenever they are coprime. So if they are coprime, then this is another way to see this property. If this is equal to 1, it means that AB is equal to the least common multiple of A and B. I would say lowest, but it's not correct. However, let us start with congruences. And as I said, unfortunately, I got aware of an unexpected concern I wasn't aware of before. And so I couldn't prepare we have to work on scratch on this notion, but it's better, of course. Maybe it's better. So now we are going to construct infinitely many new arithmetics starting from Z. What I mean by arithmetics, I mean something which is defined by a couple of tables. These two are an instance. One for the addition and one for the multiplication. So we saw the Peano's axioms, and we know because of the Peano axioms how to sum two natural numbers, and by extending the natural numbers via an appropriate equivalence relation, we got the integer numbers, and we know how to sum using that axiom inherited by the construction. We know how to sum integer numbers, how to multiply integer numbers. And of course, we can, rather than saying that 1 minus plus, so sorry, 1 plus, I wanted to say 1 plus minus 2, which is equal to minus 1. We know this, but we can produce a table which infinitely many columns, infinitely many rows, and if you put the integer I in this row, the integer j in this row, you can put in the ej entry their sum. And you can express the usual arithmetic with this infinitely sized table. But you can use also finite tables to do the same things. For instance, you can pick these three strange symbols here, 0 bar, 1 bar, 2 bar, 0, 1, 1 bar, 2 bar, both on row and columns. And this is the operation of addition in this strange set 0, 1, 2. How it is work? How does it work? 0 plus 0 is 0, 0 plus 1 is bar 1 is bar 1, 0 plus bar 2 is bar 2. 2 bar, 2 bar plus 2 bar, U stage is 1. Oh, and here 0, 0. This is quite nice. We expect this. And 2 bar times 2 bar is 1 bar. It's strange. Again. So I'm saying that this is actually an arithmetic. What I mean? I mean that it has all the properties that we expect. We can sum elements to get still elements, so they are both the addition and the multiplication. This plus and this dot stands for multiplication. Call it whatever you like, of course. So if you apply to pairs of elements this two operation, you get an element of the set. So these are operations. They have both the operation a neutral element. In this case is is the element 0, and is unique. You see that is unique. Is the only one with the property. Well, I cannot I cannot say it yet because we didn't prove, but it is true. And the operation can be extended to be associative, and this is associative because you can check it, and also for the multiplication, and also it has a neutral. You should check that every element has an inverse in with respect to the multiplication. Let us check this. So recall what is the inverse with respect to an operation. So you have the operation star with a neutral element 1, and the inverse on element A with respect to this operation is the unique element B, such that B stars A is equal to 1 stars. Assume this one is the neutral element and check that every element has an inverse. There is exactly one element that left or right multiplied by the chosen element gives you the one element. So we have to check this just, sorry, this is when there are two operations, you this neutral the inverse of an element can be defined only for those elements which are not the neutral element of the other operation. So we can concentrate on this part of the table. So it is true, 1 times 1 is 1. The operation is by definition commutative because, as you see, the commutativity can be seen from the symmetry of from the symmetry of the table, because you see here this is 1, here it is 1, here it is 2, here it is 2. It means that of diagonal elements, are symmetric with respect to the diagonal. This is commutativity. And just for completeness, these are called the Cayley tables of the arithmetic. But concentrate on this part of the table. You see that one is the inverse of itself, but those two bar as an inverse, yes, it is. Which is the inverse of 2 bar? Is itself, because 2 bar times 2 bar gives the neutral element. Something strange in this arithmetic. However, it's perfectly legitimate arithmetics. You may remember that we briefly mentioned the algebraic structure, the field structure, and this is a field on the set. These two tables give you a structure of fields on the set 0 bar, 1 bar, 2 bar, where a field is a set equipped with two operations. This is the case. We have two operations, each one having a neutral element, and this is the case because each one has its own neutral elements, 0 for the sum, 1 for the multiplication, but you can call it whatever. It does not change the meaning. Good. The addition is associative and commutative. This is the case in both cases. And each element which is not the neutral element of the addition has an inverse. So this is actually a field. We didn't say much about the reason why this why these two tables define an arithmetic, but this is what you are going to do now. But just using the table, trust me, this is an arithmetic. Use it. Just using the table, we get, for instance, the square of 2 bar is 1. We get that the inverse of 2 bar is 2 itself. And this is just what I wrote here is just the definition of inverse element here and here. But we recorded it. We recorded it a moment ago. So, how do we arrive at these two tables? It's not by magic. There is a mathematical reason, which is a very strong mathematical reason, and which is also very easy to explain. If I don't succeed, it's up to me. It's my fault. So, most of what I'm saying, we already mentioned. So, this is just a good recap. Pick two integer a and b in Z and define this relation. This is a relation because is a statement about pairs of integers. Of course, there is no need to be more formal than this. You recall what is a relation on Z? It's just any subsets of the square of Z. Just pairs, ordered pairs of integers. And we are talking about pairs of integers. So we are going to define a relation which turns out to be an equivalence relation, an important equivalence relation. We say that A is congruent to B modulo n, and we write the statement in this form whenever n is sorry, when n divides A minus B. Just a definition. A is congruent to B modulo n if and only if n divides the difference A minus B. Just explore the definition. For instance, let us fix as a modulo 3. So is 5 congruent to 7 modulo 3? I don't know. Let us check. 3 divides 5 minus 7? No. So is not. No. Not. No. Is 5 congruent to 8 modulo 3? I don't know. Let us check. 3 divides 5 minus 8? Yes, because 3 divides minus 3. So it is 5 is actually congruent to 5 modulo 3. And 8 is congruent to 5 modulo 3. It is the same things. Why? Because just, just if 3 divides minus 3, of course, 3 divides 3. And in general, this is a general fact. You should check. It is very easy to check. But let us check it together. This is a remind to do it from scratch, this dotted line that I just canceled. So what does it mean that A congruent to B modulo n? It means that AB is a multiple that n divides A minus B. But then minus 1 times I A minus B by B minus A is also a multiple of n, of course. So if you are minus 24 is a multiple of 12, of course. It is minus 2 times 12, then 24 is a multiple of 12. It is 2 times 12. So, other examples. Is 117 congruent to 7 modulo 10? It is hard to answer. So let us do in this way. Write, consider the decimal expansion of 117. You can write 117 in this way. So if, in the primary schools in Italy, these are called the hundredth digit. These are called the tenth digit. This is the hundredth digit. This is the tenth digit, and this is the digit of units. Every number, even real, not in this way, every number, even rational number, can be written using the decimal expansion in this way. as as a linear combination, linear integer combination that, on the powers of 10. Of course, binary expansion of the powers of 2, ternary expansion of the powers of 3. Of course, you can fix a base and write any number with respect to the base using these powers. We usually adopt from the primary schools fortunately the decimal expansion. I say fortunately because it's the only one that I know very, very well. So, binary expansion is not that difficult, but there are more difficult expansions. However, once you have written 117 in this way, you see that 7 and 117 are congruent to each other modulo 10. But why this is true? Because just subtract 7 from 117 to get 110. 110 is 11 times 10, which is a multiple of 10. In general, you can write any number, any integer number in its decimal expansion, and you get, of course, that any number is congruent to its last digit, the digits of units, modulo 10. So, and it's also true by the same reason, but you must experience this by trying to convince yourself that this is true. It is also true that modulo 100, every number is congruent to its the number formed by in this order to the number formed by its two last digits. So the digit of units in the digit of tens. And you can go on and generalize to modulo any power of 10, getting similar results. So let us work out the example. So this is too long to pronounce even in Italian, this number. If you take the difference between these two numbers, it is 758 times 100. And so actually the two numbers are congruent to each other modulo 10. I say they are congruent to each other because we proved that A congruent to B modulo n if and only if B congruent to A modulo n. So we already proved that whatever it is, this relation, it is symmetric. And indeed, it is an equivalence relation on Z because it is clear that any integer number is congruent to itself because every modulo divides 0, which is the difference between the number and itself. So it is trivially reflexive. We already have shown that it is symmetric, that is A congruent to B modulo n if and only if B is congruent to A modulo n, and is trivially transitive. because if A is congruent to B, this means that B minus A is a multiple of N. If B is congruent to C, this means that C minus B or B minus C, whatever you like, is congruent to is a multiple of N, then A minus C is a multiple of N. How to see this? Just use this obvious trick. Write A minus C as A minus B plus B minus C. And observe that on the right hand side there are only multiple of N, therefore their sum is a multiple of N. The most interesting question about this congruence, this relation, which is called congruence modulo N, recall it, is the shape of its equivalent classes. And we already mentioned this shape. So here there is another equivalent way to express the congruence. Saying that A is congruent to B modulo N means that A minus B is, you should recall this. This one. You should recall this set. However, if you don't, I just write it. It's the set of multiple of of N. So saying that A is congruent to B modulo N is the same as saying that A minus B is a multiple of N, is the same as saying that I minus B is in NZ. So A, B are in the same equivalent classes if and only if the difference is a multiple of N. So we should show that the equivalent classes of congruence modulo N are precisely the set which are listed here and which I'm going to highlight. And we will prove this. However, we already did some experiment with these sets. We called it lateral classes, and now these are indeed lateral classes modulo N, but this doesn't matter. However, we will see it in a moment, in a while, but if this is true, and it is true, as we will show, recall that the set of equivalent classes of an equivalent relation is called the quotient of is called the quotient of the set by the relation. So the quotient of the congruence modulo N is the set of sets. Classes are sets. Before putting this representation, let us check, for instance, that so if A and B are congruent modulo N, they belongs to NZ, but if they are not, what does it happen if A is not congruent to B modulo N? For instance, if A belongs to 1 plus N minus it, Recall that 1 plus n minus it, n times it, sorry, n times it is a set, and is precisely the set consisting of those integers that differ by a multiple of n by 1, are displaced by 1. The multiple of n displaced by 1. And 2 times nz, 2 plus n times z, nz is the set of multiple of n displaced by 2. So these are not congruent modulo n because they belong to different classes. And indeed, this is true because if you saying that A belongs to this class means that A is equal to a special, a picket, especially picket multiple of n plus 1, and B is a specially picked multiple of n plus 2. Just solve the just do the operation. B minus A is equal to 2 minus 1 plus a multiple of n. So B minus A is not in NZ as as should have been if they were congruent. It is in another class. It is in the class of 1 plus nz. Here is the explanation, which is something which I think we already know, but let us do it again. We have this following fundamental observation, key observation. A is congruent to B modulo n if and only if A and B, when divided by n, give the same remainder. Let us convince ourselves that this is true, and suppose that when they divided by n give the same reminders, suppose that A and B, when divided by n, give the same reminders. So there are Q and P such that A is equal to Q times n plus R, and B is equal to P times n plus R. This is the definition of Euclidean division. If you divide A by n, you get a remainder R. If you divide B by n, you get another remainder R prime. In this case, we are saying that the remainder is the same. It's not the quotient is not necessarily the same. Otherwise, the two numbers, due to the unicity of the representation, would be the same. They are not necessarily the same, the quotient, but the remainder we are forcing to be the same by assumption. They are the same remainder. So just pick the difference, A minus B. What is the difference? Is a multiple of n. So the difference is in nz. Therefore, it is true that if A and B give the same remainder when divided by n, they are congruent to each other modulo n. Trivia. Sorry. The converse statement is not so trivial, however, it's not difficult. Just assume that just pick two such representation now with two different reminders, not necessarily, but differently denoted, R and R prime. Uh, Probably it's better to do so. We are assuming now that the two numbers a and b are congruent to each other modulo n, and we want to show that when divided by n, they give the same reminders, but we cannot write it directly because it's precisely what we want to show. So we have to write these two, no, sorry, these two representation. And this time we want to prove that R and R prime are the same number. So, but we know something. We know that A is congruent to B modulo n. So A minus B is an NZ. If you do if you do the easy computation, you see that this means that R, this means that R prime minus R should be in NZ. But you know that R minus R prime or R minus R prime minus R are always smaller than N. So since they belongs to the set of multiple of N, but they are smaller than N, what is the unique possibility left? Is that R minus R prime is 0, is the unique multiple of N, which is less in absolute value, which is less than, which is smaller than N. So try to convince yourself that this is true. Pause and think a little bit more on this fact. But after fact one, this representation is proved because this is obvious. Of course, each one of these classes is defined by a number plus a multiple of n. Since two numbers are congruent modulo n if and only if they give the same reminder when divided by n, and there are only n possible reminders, which are these reminders are 0, 1, 2, up to n minus 1. We have proved that this representation holds because, for instance, look at this one. This consists, it is precisely the set of integers that, when divided by n, give reminder 2. This is precisely the set of integers that, when divided by n, give reminder 1. 4 plus nc is precisely the set of integers that, when divided by n, gives reminder 4. Since the largest possible reminder of the division by n is n minus 1, it is clear that this representation, these sets of sets, is precisely the quotient of z by the congruence modulo n. And there is this bijection. So, Each one of these classes is uniquely determined by the remainder of the one of the remainder of the division. So due to this bijection, due to this representation, due to this algebraic meaning, we can just represent these sets that are indeed sets with these symbols. Just put over the remainder an overline. Yes, it's hard to explain. Good. So let us summarize. We introduced this relation. We did some experiment about this relation. We get familiar with this symbol. We know in special case what it means. For instance, we know what is the congruence modulo 10. In general, congruence modulo n is the property that the difference of congruence number is a multiple of n. Good. We saw that this is not a trivial relation, it's a very strong relation, it's indeed an equivalent relation. We prove it very easily because the conditions are easily checked. Then we ask ourselves, well, what is the quotient? Since this is an equivalent relation, is it meaningful to? It is meaningful to ask the shape of the equivalent classes of the equivalent relation, and we found out that the class of the equivalent relation are this very nice and now well-known shape. These are the multiple of n plus the multiple of n plus 1, the multiple of n plus 2, the multiple of n plus n minus 1. Why not the multiple of n plus n? Because the multiple of n plus n is the same as the multiple of n. The multiple of n minus 1 plus 3 is the same as the multiple of 2. And so we, with this observation, we also understand or start to advise a way of define operation on this new symbol. Recall, why should I stop with m minus 1? Why can not why not n minus n sorry, not n minus 1, m plus 3? Why not m plus 3 plus nz? Because this is already counted, this is already in the set m plus 3 plus nz. What is? It's just 3 plus nz. But 8m plus 3 plus nz, what is? This is a multiple of n, so it is already in. What is left? 3. And indeed, it is the remainder of the division of 8 times n plus plus 3 by n. Here it is, for instance, a useful but trivial observation. It is always true that if you take A, you add to A n, you get a number which is congruent to A, because The difference is clearly a multiple of n. This is essentially what explains this structure. So other trivial observation, but this is something more formal which I have to realize. So pick an integer a. There is another way, probably more intuitive, to denote the equivalent classes modulo n to which A belongs to. So if I write an, I am meaning the set of all B in Z such that A is congruent to B modulo n. So when I write this symbol, when I write this symbol, I'm just writing the equivalence class to which A belongs to. I don't know what is so far, but one surely exists because the equivalence classes gives a partition of Z. So A is certainly in some equivalent classes and in some equivalent class, and this symbol is the one that selects the equivalent class to which A belongs to. Good. So once we have understood this symbol, we can easily deduce a generalization of what we notice here. So the equivalent class of A plus a multiple of n modulo n is the same class as the class of A. That means that if you pick an integer this integer belongs to some class because the class partition Z. Pick an integer in this class. You remain in the same class whenever you have to this integer a multiple of n. And which one is this class? Is the class containing the remainder of the division of A by n. Good. Now let us do some experiments because otherwise it can be really tough. So, for instance, what is the class of 7 modulo 4? This is the same as the class as 3 modulo 4, which is 3 bar, for instance, in this notation, in the extended notation. The notation, the explicit notation of the quotient. So, say the class of 7, I'm sorry if I insist, because I'm insisting on the class of you. For the time being, you have to understand very well that we are speaking about sets, not numbers. We are still speaking about sets. But we already have an idea to introduce operation on these sets. our our aim is to build an arithmetic on these sets, and we are on the good way to do that. So the class of 7 modulo 4 is the class of 3, is the same as the class of 3 modulo 4. Let us try to introduce an operation, for instance, the multiplication of two classes. Pick the class of 2 and the class of 3 modulo 4. So the class of 2 modulo 4 is denoted in this way. The class of 3 modulo 4 is denoted in this way. So what are we doing? We are picking this class, multiplying by this class. What kind of meaning can this result have? So if I pick one element in this set and one element in this set, and I multiply these two elements, which are numbers, I can do that because what I get, I have 2 plus a multiple of 4 plus 3 plus a multiple of 4, a different multiple, of course, probably, likely. Not the only thing is they are not necessarily the same. So let us do this small count 6 plus. Now, don't let me skip because look, 2 times 3 and all the other terms are obtained by multiplying one 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 of the elements in the first bracket by one of the elements of the other bracket. We already did the first pairing. All the other pairing contains at least are multiple of 4. Let's do that. The bar 2 times bar 3 is 6. No, sorry, this is not bar 2. Why I wrote? No, this is 2. Let me write it better. Sorry, guys. I'm going to be tired, and maybe you as well, but hold on, please. So we started with this idea. We want to give a meaning to the product of these classes. The most natural way is to pick an element in the first class, multiplied by an element, a picked element, or in the other class, and see what it happens. Of course, you may object, and you and you will be right. This is not an operation because it depends on the picked element in the first set and on the picked element on the second set. If I change the element chosen in the first set and the element chosen in the second set, at least one of the two elements, the result would be different. Actually, you are right, it is different, but it is different in a way that is not essential. We will see. So pick an element in the first set. This is not an equal sign. Pick an element because we are defining we cannot write equal because it's not an operation yet. Pick an element in the first set, an element in the second set, multiply, and see what it happens. So an element of the first set has the form 2 plus a multiple of 4. And in the second set is 3 plus a different, is not necessarily the same multiple of 4. Let us expand 6 by plus q prime 8 plus q12 plus q prime. Good. You see, here this is 6, which is 2 by 3. Here there is a multiple of 4. Here there is a multiple of 4. Here there is a multiple of 4. So I can say that this element, this product, belongs to 2 times 3 plus 4z. The question is it true for every element? Yes, it is true for every element. The elements, the result would be different. No doubt about this. The result would be different. However, the structure is the same. Every result, every number resulting from this multiplication is always of the form 2 times 3 plus a multiple of 4. So I can, if I put 4z, I don't remember, was 4? Yes. 4z times 3, 4z I define an operation, a multiplication between classes, which does not depend on the particular element chosen in the first set and the element chosen in the second set. Therefore, this is well defined, well posed, this definition. But what is this? This is just the class of 2 modulo 4, and this is the class of 3 modulo 4. And this is what? The class of 2 by 3 modulo 4. And you can write it differently in this way. And what is? This is the class of 6 modulo 4. But what is the class of 6 modulo 4? Apply the definition, apply the characterization. The class, here it is. The class of A modulo n is exactly the class of the remainder of the division of A by n. So if R is the remainder, the class of A modulo n is the same as the class of R modulo n. So what is the class of 6 modulo 4 is the same as the class of the remainder of the division of 6 by 4. And which is this remainder is 2. So this is what we get. The results, modulo 4, sorry. The results of this operation is exactly the class of the product of the classes is exactly the class of the product of the elements. So the product of the classes of two particular integers modulo 4 is the class of the product, is the class modulo 4 of the product of that particular integers. The same is true for the sum. If you pick by the same reason, again, by much easier, but by the same reason which we are given for the product, all for the sum. So the strategy is to pick one particular element here and one particular element here, to sum this particular element, to observe that modulo, they can be written always in the form of the sum of the elements plus a multiple of 4. So the results is always, this is actually, now which have defined the operation, this is actually an equality sign. And then plus 3 modulo 4, the sum of the classes of two particular elements is equal to the class of the sum of that of those particular element. But what is the class of a particular element? Is the class of its remainder, or the remainder of that particular element when divided by the modulo. So what is the remainder of 5 divided by 4 is 1. And you can write it in this way. And so in this way, you already filled a part, for instance, of this table. So we are in Z4. We are working modulo 4. The possible reminders are 0, 1, 2, 3. 4 is 0. And so we know that this is 1, and that this is the multiplication. This is the sum. Last thing, what was the result was 2. So by exercise, fill completely the table and solve the arithmetic of zeta 4. Good. Thank you guys for your patience, because it was long and hard today. I'm going to upload everything we did so far. So good evening, and see you next time. Ciao, ciao.
Ciao.
Ciao, good evening. Goodbye.
Goodbye.
Bye.
Bye bye. Good.